Hello everyone, and welcome back. Today we're going to continue our exploration of multivariate statistics and introduce a new metric that's going to help us calculate distances from, for example, the mean vector for a multivariate distribution. Let's first go over some basics that you definitely need to know in order to understand this topic. So let's assume that x is a random vector with random variables x1, x2, all the way down to say xk. So we say that x is a multivariate variable, or x is a random vector, where each of its elements are random variables. Let's also suppose that x is a multivariate normal random vector. So if it is a multivariate random vector with, let's say, mean vector mu and covariance matrix, let's call it sigma, then the probability density function of x with particular values x1, x2, all the way down to say xk, is going to follow the following density function. 1 divided by 2 pi to the power of k divided by 2, and then the square root of the determinant of the covariance matrix, times e to the power of minus 1/2 x minus mu to the power of t, or transpose of that vector, and then the inverse of that covariance matrix, and then x minus mu. So that is the probability density function for a multivariate random distribution. So a couple things that is here in case you aren't familiar with it, where the variance of x, which is the variance of the vector x1, x2 down to xk. Keep in mind the variance of a random vector is going to be a matrix. In particular, it's going to be a k by k square matrix, and we usually represent it by sigma. And also the generalized variance of x is also sometimes defined and denoted by the determinant of that covariance matrix. Obviously, if you want the trace of that covariance matrix, that would be the total variance of that random vector. Let's talk a couple theoretical things about the covariance matrix and its determinant that you probably should know at this point, but if not, let's just mention it just in case you don't. So one theorem that you definitely should know is the following. So if sigma is truly a covariance matrix, and when I say truly a covariance matrix, I don't just mean a matrix of covariances. I mean a covariance matrix in terms of its structure, not just its elements. Then its eigenvalues are all non-negative. So all of its values are non-negative. That means they can be 0 or they can be positive. So we of course can write that as lambda j is greater than or equal to 0 for j is equal to 1, 2, all the way down to k. So if you already have your eigenvalues calculated, then you can express a lot of these metrics in terms of its eigenvalues. In particular, the variance, the generalized variance of that random vector x, aka the determinant of the covariance matrix, since these lambdas are the eigenvalues of that particular matrix. Then we can represent the determinant as just the product of its eigenvalues, in particular lambda 1 times lambda 2, all the way down to lambda k. Or in product notation, the product from j is equal to 1 to k of lambda j. Also, if you have the eigenvalues, you can also represent the total variance in terms of its eigenvalues as well. Keep in mind the total variance of a random vector is defined to be equal to the trace of the covariance matrix, which is just sigma 1 squared, sigma 2 squared, all the way down to sigma k squared, all added up. But if you have the eigenvalues, one can show that that's precisely equal to lambda 1, lambda 2, all the way down to lambda k. So if you equate those two statements, in some sense, the variances are the eigenvalues in disguise. Now, let's talk a couple numerical things in terms of the graphical picture that you definitely need to understand in order to understand what is called the Mahalanobis distance for a vector. So let's recall a couple things. Let's suppose that xi and xj are random vectors are such that they have variances. Let's call sigma I squared to be equal to 5, sigma j squared to be equal to 7, and let's assume that the correlation between I and j is equal to 0.875. So if it's a positive correlation, if you look at its scatter plot and its data points, then you should see a bunch of data points sort of correlated in the positive direction. And if you were to trap this inside of an ellipse, because we should know at this point that the shape of a multivariate distribution is elliptical. So therefore there exist these axes that can practically trap all of the data inside of that ellipse. So we've already discussed that these directions for these vectors, for example, this vector here and that vector there, are dictated by the eigenvectors of your covariance matrix, in particular eigenvector I and eigenvector j, and the lengths of them are corresponding to the eigenvalues I and eigenvalue j. So in this particular case, we have that sigma j squared is equal to 7, and let's just label our axes. So let's assume that this is xi, and this is xj. Since the correlation is not equal to 0, the principal axes will not be on the horizontal and vertical axes, right? Because if the correlation is equal to 0, technically speaking, the eigenvectors are always orthogonal, but they're not, for example, the unit vectors per se, i.e. 1, 0, and 0, 1 in the I and j direction. But if the correlation is non-zero, the eigenvectors still will be orthogonal, but they're not going to be along the horizontal and vertical axes, right? So in this particular case, we have the longer case associated to the larger eigenvalue. So that means this is going to be eigenvalue lambda j, and this shorter eigenvalue is going to be associated to lambda I. And obviously that vector there is going to be associated to eigenvector I, and this vector here is going to be associated to eigenvector j. Because when the correlation is not equal to 0, those lengths could correspond to either variable I or variable j, so you have to consider the lengths in order to figure out which one is which. Right? So that's pretty much the basics of the geometry of a multivariate normal distribution. Now let's introduce a couple metrics in terms of distance. In particular, the most famous of them all probably would be Euclidean distance. So Euclidean distance considers all the points in a circular manner. So let's assume that we have, for example, variable xi and variable xj, and let's draw a couple circles in this data set. So let's also plot a couple points here. For example, let us assume that this point right here is the point mu. So 0, 0, generally speaking, if you standardize it, but mu x, mu y, or mu I and mu j is going to be the coordinates of this center, generally speaking. So let's choose a point right here, and let's choose a point right here. Notice that they lie on the same exact circle, therefore their shortest distance in the plane is going to be the same, provided that the shape is a circle, of course. So we can call, for example, this point A and this point B, and let's assume that we choose a couple points, for example, C, and for example, let's assume we choose that point D. Notice that they lie, again, on the same exact circle, right? In particular, a radius of, say, 3 or something like that. So we can clearly see that those have the same Euclidean distance. So we can write a couple things here. For example, you can say that the Euclidean distance, which we're just going to be writing as d2 of AB, is equal to what? So if we write this in matrix form, you can write this as A minus mu transpose. Actually, let's write A in terms of the vector mu. I think that's a little bit more useful. So the distance between A and mu is going to be equal to A minus mu transpose times A minus mu. You could also write the d2 distance between A and B as the square root of A minus B transpose times A minus B. Keep in mind, A and B are vectors. For example, if D corresponds to the point 3, 2, then that's corresponding to the vector 3, 2, and R2, right? And obviously, if we're in higher dimensions and we're just looking at a two-dimensional projection of that space, obviously you're going to have a few zeros in play here. Or you can just consider all of the components in k-dimensional space if you want to, and that is perfectly okay. Now, if this representation of distance is not familiar to you, for example, let us assume that A is equal to xi, yi, and let's assume that B is equal to xj and yj, then this representation actually can be found to be equivalent to the square root of xi minus yi, the distance between the horizontal components and then squared, and then plus xj minus yj, the quantity squared. Right? And you can prove that that is truly the Euclidean distance by using some right triangle geometry. Now, keep in mind that if x is associated to a multivariate normal distribution whose mean vector is mu and covariance matrix is sigma, then the two-dimensional projections of the multivariate distribution are not necessarily circular. So that's very important to keep in mind. So it's not necessarily circular. And it's only circular, it's a circle, if and only if the correlations between I and j are equal to 0. That is, they're independent in some sense. So if they are not circular, then they, of course, will be elliptical. So let's take a look at that in the distance metrics associated to it. So let's assume that sigma I squared also is not equal to sigma j squared, and let's assume that the correlation also need not be equal to 0, right? So if the variances are not equal to each other, then the shape is elliptical, and if the correlation is not equal to 0, that means the semi-major axes, so the semi-major axes are not equal to the principal axes. Actually, I don't want to use the word principal. Let's say the coordinate axes. I think that's a little bit more safer. Right? So, shape is elliptical means that the variances, aka eigenvalues, are not equal to each other, and correlation not equal to 0 means that that ellipse is sort of tilted up or tilted down. So let's assume that both of these are the case. So that means our trajectory is going to be something along this sort. So let's assume that that's one ellipse, right? So there's our twice eigenvector, I guess you could say. Now, keep in mind, eigenvectors are not unique. You can scale them and still be eigenvectors. So therefore, we can actually have another one right here, right? And obviously, we can extend that a little bit and have another ellipse outside of that, right? But generally speaking, there's one eigenvalue and one eigenvalue for the other one. So let's assume this is, for example, xi, and this is xj. Right? So if this is the picture, what exactly do we have here? So let's choose a few points here. So let's choose, for example, that point A and that point B on the same exact ellipse. And let's choose this point C, and let's choose this point D. Now, if I consider the Euclidean distance between, for example, D and mu, and D and C, at least in this picture you could see that the distance between mu and C and the distance between mu and D are not equal to each other. In particular, it appears that C is a little bit more farther than D is. And if we consider the points, for example, A and B, they're about the same distance, but A appears to be a little longer. But nonetheless, D and C are on the same exact ellipse, and A and B are on the same exact ellipse as well. But we clearly see that the L2 distance, or the Euclidean distance, between C and D, actually let's use mu as a point of reference, is not equal to the Euclidean distance between D and mu, right? Because if I were to draw a circle around D, C does not lie on that circle, right? So we can say that this is true if and only if C and D do not belong to the same circle centered at mu. But C and D do belong to the same ellipse. And we know that the shapes of the projections of a multivariate normal distribution, in the general sense, are elliptical. So comparing distances with circles is technically unfair for a multivariate normal distribution. So is there a way to measure elliptical distances rather than circular distances? The answer is, of course, yes, and that's what we refer to as the Mahalanobis distance. Right? So the star of the show will be Mahalanobis. Mahalanobis distances. So the Mahalanobis distance will weight the distances with respect to their associated variances. So I'm going to be representing the Mahalanobis distance as dm, And let's consider the distance between some vector x and some vector mu. And this is going to be equal to x minus mu transpose times the inverse of the covariance matrix and then x minus mu. So in terms of the dimensions, obviously this vector here is a 1 by k, this is going to be a k by k, and this is going to be a k by 1, and that's obviously going to result in a 1 by k because their inner dimensions definitely do agree, right? So that is just a number, and hence the distance will be a number too. So the main difference, at least on the formula side, between Mahalanobis and Euclidean distances is that Mahalanobis takes into account the variance of those associated variables, right? And obviously, if that is the identity matrix, i.e. it's standardized and the correlations are equal to 0, then you're back into the Euclidean distance world, right? So if your xk's are standardized, let's call them xj's since we've reserved k for the dimensions. So xj is standardized, and let's assume that the correlation between I and j are all equal to 0. Then we see that, for example, the covariance matrix is just equal to the correlation matrix. The second correlation matrix will then be equal to the identity matrix. And obviously, when I invert that, that's just going to be equal to the identity matrix. And hence, the Mahalanobis distance between x and mu will be equal to the Euclidean distance between x and mu. In particular, that's the only case. Right? So we get that at least algebraic result into it. So how do we consider this from the geometric point of view? So obviously our correlations need not be equal to 0 and our variances need not be equal. Therefore, these elliptical shapes will definitely not be circular. But if that is, for example, a particular ellipse, and you have this point here and this point here, which obviously have different L2 distances, different Euclidean distances, right? Because as long as those eigenvalues are not equal to each other, the Euclidean distance between A and B is not equal to each other. You can sort of draw a circle here and sort of convince yourself of that. But we clearly see that the Euclidean distance between A and mu is not equal to the Euclidean distance between B and mu, but the Mahalanobis distance between A and mu is equal to the Mahalanobis distance between B and mu, which actually makes sense in terms of comparing how far a point is to the mean with respect to its variance. Now, in terms of these distances, because we already know a formula for distance, you can actually find that if you take your Mahalanobis distance formula between, for example, x and mu, let's assume that x is a random vector, and let's assume that mu is a constant. And let's consider its formula again, just in case you forgot. So x minus mu transpose times the inverse of the covariance matrix times x minus mu. This is actually going to follow a chi-k distribution. And if you're not familiar with the chi distribution, that's perfectly okay because we can square both sides of this statement. So we could also say that the squared Mahalanobis distance between a random variable and a constant vector, which is just x minus mu transpose, inverse of the covariance matrix times x minus mu, without the square root, this will follow a chi-squared k distribution. And you definitely should know by now the chi-squared distribution. But you can work directly with the Mahalanobis distances without squaring if you do know the chi distribution. So what exactly does that mean from the statistical point of view? Well, we already know that the chi distribution has this particular shape, so that's going to be our chi-squared k distribution. So having points that are super close to the mean are definitely less likely than, say, points that are within, say, 1 z-score or 2 z-scores from the mean, which is where the majority of the density function is going to be located here, right? But there are a couple important things that you definitely should know in terms of Mahalanobis distance, z-scores, and the multivariate normal distribution. And also some connections to other metrics that you definitely should know as well. So let's actually go through each of them and see if we can build a nice story out of that. Now, in case you haven't already noticed, we have actually seen this formula for the squared Mahalanobis distance already. This is actually not that new at all, because it's actually in the exponent of our multivariate normal distribution. Because remember, our multivariate normal distribution has the formula 1 divided by 2 pi to the dimensions divided by 2 times the square root of the determinant of the covariance matrix times e to the minus 1/2 squared Mahalanobis distance. So we can actually rewrite this as the squared Mahalanobis distance between our random vector x and mu, and that's an equivalent representation. And if you compare this to the k is equal to 1 case, which is 1 divided by sigma, the square root of 2 pi, e to the minus 1/2 zx squared, we can clearly see from this that Mahalanobis distance and z-scores are actually the same exact thing. So Mahalanobis distance can be viewed as a multivariate z-score for a particular vector, which is actually quite interesting. Right? So if we can use z-scores to determine outliers in the univariate case, we can determine outliers in the multivariate case with Mahalanobis distances. Now, if you get really far from the mean of the distribution, for example, if you look at zx, which is going to be equal to x minus mu over sigma, as you get farther and farther away from the mean of that distribution, the z-score is going to get extremely large. So there was another metric that we introduced back in multiple linear regression that actually allows us to pick up on this exact thing. So let's just briefly revisit multiple linear regression to sort of see what that was. So remember that the predicted values was equal to the design matrix times our beta hat point estimates. Let's assume we're using least squares regression, for example. So what was the beta hat solution for that particular problem? Well, beta hat came out to xtx inverse times xty. And again, keep in mind that x is an n by k plus 1 design matrix, where we have n responses and we have k plus 1 points, in particular k predictors. So if we replace this beta hat formula inside of the prediction calculation, then we have that y hat is just going to be equal to x times xtx inverse times xt times y. And we can actually just call this matrix a new matrix, in particular h. So if we take y and we multiply it by h on the left, we get y hat. So sometimes this matrix h is called the hat matrix. And this hat matrix actually stores a bunch of information, but keep in mind h only depends on x, right? So if you remember, we defined a metric known as a leverage for response, say, I, and keep in mind the hat matrix H is an n by n matrix, so it's only focused on the response, not the number of predictors or dimensions in our case, right? And the leverage was defined to be equal to the diagonal entries of that hat matrix. And what exactly was a leverage and how did we interpret it? Well, it was just a weighted distance from the average values. And just because a point has a high leverage does not, of course, mean it is an outlier. Because if you remember our data points, right, let's assume that we have some point way over here. So obviously x bar is located there. It's slightly dragged to the right because of that outlier. If we fit a line to this data point, that point sort of fits exactly on our line, right? But the distance in terms of its location and the majority of them is really large. So if it happens to be an outlier, like way down here, it's actually going to skew your line a lot, which is actually a really bad thing. So we sometimes say that that's a good large leverage point, or a good leverage point, just to keep things short. And that would be, for example, a bad leverage point, right? And you can say that bad leverage points would be outliers. So that's practically what's going on here with Mahalanobis distance, except it's just a different perspective. It's a different unit as well. So, is there a theoretical connection between these things? And the answer is, of course, yes. One can find that the Mahalanobis distance for your jth response is actually going to be equal to n minus 1 times the jth leverage minus 1 over n, where n is the number of responses in your sample. And obviously you can solve this for the leverage, and you can write this equivalently as Lj is equal to 1 over n plus the squared Mahalanobis distance, the jth one, all divided by n minus 1. So obviously there is a very close connection between Mahalanobis distance and leverages, which is obvious from these particular points. Now, there's a very interesting point, and you should already know this from our previous discussion on univariate z-scores, because if this is a normal distribution, and let's assume that this is the mean, then we have mu minus sigma there, mu plus sigma there, and that's associated to these points for which the convexity of this curve changes. So here it's a concave up curve, here it's a concave down curve, and here it's a concave up curve, right? And in particular, these are our inflection points. And if this is a standard normal distribution, then this is actually equal to mu, that's equal to minus 1, and that's equal to plus 1. Right? So if we extend this into the multivariate case, we can clearly see that the points for which the squared, or the original Mahalanobis distance between x and mu, is equal to 1, correspond to the multivariate inflection points. And what exactly does that look like in higher dimensions? Well, if you sort of draw a higher dimensional curve, right, let's assume that that's the peak, and let's assume that, for example, the curve sort of looks like that, and let's assume that the other dimension sort of looks like that, and we have just a bunch of sort of ellipses hanging out here. So if you calculate the points for which the Mahalanobis distances is equal to 1, which is going to be on one of these ellipses, right? So obviously the smaller Mahalanobis distances are going to be on that blue ellipse, a larger Mahalanobis distance is going to be on that purple ellipse, an even larger Mahalanobis distance is going to be on that red ellipse, and it's going to sort of go downwards, right? Let's assume that's, for example, mu x or mu y. So the points for which the Mahalanobis distance is equal to 1 actually corresponds to the points where that hyperdimensional ellipsoid is actually concave down. So we can actually create a nice little summary chart. So if the Mahalanobis distance for a particular point to mu is less than 1, then it's concave down at that particular location. And if it's equal to, actually, or just strictly greater than 1, then we say that it's concave up. Now, obviously, the words down and up don't have the same dimension like it does in univariate world because we're in multi-dimension, so it's down with respect to what or up with respect to what. But nonetheless, the convexity is down and the convexity is up in terms of each of these cases, right? So those are some very important things that you definitely should know. Now, since we know that the squared Mahalanobis distances follow a chi-squared k distribution, we actually can do quite a few probabilities with Mahalanobis distances, and there's definitely a few that I want to mention here that are very important. So let's consider the k is equal to 1 case, so the one feature case. So what is the probability that the Mahalanobis distance squared, or Mahalanobis distance, is less than 1? So you can consider a chi-squared 1 distribution and do the probability from 0 to 1 in integral form or numerical form, either is fine, and that's going to come out to approximately 0.6827. And this should look very familiar because that is the same exact 68% as from the empirical rule that we typically memorize in, say, baby statistics. Now, if I increase the dimension to 2, will the percentage of points that is within 1 Mahalanobis distance from the mean be the same? Will it be higher? Will it be lower? So one can directly find that. So what's the probability that the squared Mahalanobis distance is less than 1 for a two-dimensional feature space? One can find that that's going to be approximately equal to 0.3935. So it's less. Well, is that really the case for all higher dimensions? So we can consider the case when k is equal to 3. So what is the probability that the squared Mahalanobis distance is less than 1 in 3 feature space? That's going to be approximately equal to 0.1987. In particular, you will see that these probabilities will decrease to 0 as the number of features goes to infinity, right? In particular, you can interpret this as, well, our points have more dimensions to explore, so they're not going to be situated around the average as much. But if they're not near the mean, where are they? And that's a very interesting question. So let's actually look at another geometrical thing, and it's actually going to help us figure out what's going on here. So let's consider the volume or the hypervolume of the ellipsoid. So the hypervolume of the ellipsoid. So for k is equal to 2, in particular 2 dimensions, the volume of the ellipsoid is equal to pi times the product of the semi-major axis lengths, so L1 and L2. So if I were to draw a picture of an ellipse, let's assume that this distance is, for example, L1 and that distance is L2, and it's centered at a point, it doesn't really matter where, then the volume, or the area, I guess you could say, is equal to pi times L1 times L2. And volume, hypervolume in 2D is just area. Right? Now keep in mind, we can actually represent this as the product of the eigenvalues now. So we can actually write this as pi times the square root of lambda 1 times lambda 2. Right, so that's the 2-dimensional version. So if we can increase the dimension to k is equal to 3, one probably knows that the formula of a 3-dimensional ellipsoid is going to be equal to 4/3 pi times the square root of lambda 1, lambda 2, lambda 3. Now, nice fun question. Is there a general formula for an arbitrary k? And the answer is, of course, yes. So if you know the gamma function, you can actually have a nice representation of this. So the hypervolume of a hyperdimensional ellipsoid is given to be pi to the power of k over 2 divided by gamma of k over 2 plus 1, and then times the product from j is equal to 1 to k of the square root of lambda j. Right? And some people will rewrite this as a gamma of k over 2 times k over 2 in the bottom, and then put a k on the bottom and a 2 on top. But I like this form a lot more because then it's not as easy to forget your 2 in the top. Now, one very interesting thing is this. Notice that the top of this expression is an exponential function, and the bottom is practically a factorial, which, if you know anything about Stirling's formula, is practically like x to the x, where the top is like 2 to the x. And we know that tetrations will grow a lot faster than exponentials. So if we treat each of these lambda j's to all be equal to 1, all of them, then we should be able to graph the volume for a bunch of different dimensions, including ones that aren't integers. So one can show that for a 0-dimensional ellipse, the answer will be 1. So a 0-dimensional ellipse will have a 0-dimensional area of 1, whatever that means. And the volume will appear to increase, but after some point, it actually disappears. And in terms of where this point is, if you're choosing all of your lambdas to be approximately equal to 1, this is approximately equal to 5.26. So after 5 dimensions, if you keep on increasing and increasing your dimensions, the volume of your ellipse will actually decrease, right? And it will go to 0, right? So it practically disappears. Even though you're adding dimensions, it's getting smaller in size, which is actually very strange. And back to the other question that I posed, if they're not getting close to the mean, where are they going? They're actually getting closer and closer to the boundary, which is actually very interesting. But I won't prove that for this particular case. But it's an interesting geometric thing to think about and also ask why about. The last question that I want to end with today is more on the end of hypothesis testing. Can we approximate where the true ellipse is for, say, a 2-dimensional projection of our data from our hypothetical sample ellipse? So we have our points in 2-dimensional space, say for variables xi and xj. Obviously, we're going to have an eigenvalue I and an eigenvalue j. We're going to have an eigenvector I and an eigenvector j. So there's definitely going to be some ellipse that's going to fit this data based on our covariance matrix. In particular, that's going to be generated from a sample covariance matrix. Now, if we were to sample all of our points, it's guaranteed that the true ellipse is not going to be associated to this ellipse, right? Because, for example, our true ellipse possibly could be associated to that location, because in some sense, we're trying to estimate sigma with our sigma hat, but indirectly, we're trying to approximate the ellipse in blue with our ellipse in red. So, to guide this discussion, let's assume that the middle of this axis is x bar I and x bar j, because we're also going to be using that to approximate, for example, mu I and mu j, and approximating mean vectors is definitely something we're going to get into in the near future, right? And why do we use xi to approximate mu I and xj to approximate mu j? Well, obviously, because the expected value of x bar I is equal to mu I, and the expected value of x bar j is equal to mu j, and moreover, the expected value of the random vector x bar is equal to the parameter vector mu, which we've already proven, right? So if we have our sample covariance matrix, which is going to be, for example, the variance of xi, xj, and all of the other things, obviously if this is a sample set, then this is going to be a sample covariance matrix. And why is this okay to use? Well, one can also prove that the expected value of sigma hat is equal to sigma, i.e. the sample covariance matrix is an unbiased estimator of the population covariance matrix. So from this particular thing, we're going to have some eigenvalues, right? So we're going to have, for example, lambda I and lambda j, but these are not the true eigenvalues. They are approximates for those eigenvalues. And these are estimates for lambda I and lambda j, where these eigenvalues are associated to the true covariance matrix, which we don't know. And obviously we have eigenvectors from sigma hat that are approximations for the eigenvectors of sigma. Agreed? So keep in mind that these eigenvalues represent elliptical distances, provided that we're sampling from a multivariate normal distribution, of course, right? Obviously, if you break that assumption, then none of this holds, right? So normal is always a good starting point. And elliptical distance has a nice metric associated to it. That's just Mahalanobis distance. In particular, you can just use the Mahalanobis distance and associate that with, for example, a chi-k distribution, or the squared Mahalanobis distance is associate that to a chi-squared k distribution. Either one is fine. Both are equivalent. So if those are associated to a chi-squared, maybe we can also create, for example, a prediction ellipsoid, I guess you could call it. So a prediction ellipsoid has, for example, semi-major axis lengths. Let's call it, for example, L hat j, because it's not the true semi-axis major lengths, because they could be longer, they could be shorter, they could be the same size, we don't know. And that's obviously going to be equal to the square root of lambda hat j, but we have to stretch this out based on our level of confidence. And since we know that these variances are associated to chi-squared random variables, then we can multiply this by some chi-squared k factor, and that's obviously going to be dependent on some alpha value that you choose. Now, obviously for each of these features you can have a different alpha value, but most of the time you should be choosing the same or a weighted average of each of them. And there's some theoretical reasons and statistical reasons why we do so. But if these alpha j's are the same, then this formula can actually be represented in a nice way. So generally speaking, the volume of the prediction ellipsoid will be equal to pi to the k over 2 divided by gamma k over 2 plus 1 times the product from j is equal to 1 to k of the square root of lambda hat j times chi-squared k of our alpha j. That's the general form. But you should not be choosing different alphas because it's possible that you make it circular when it shouldn't be. But let's assume that you choose the same alpha because that's just technically the safer thing. So that means we have the square root of chi squared times the square root of chi squared times the square root of chi squared, k times. And that's if same alpha for each. Then we're going to have pi to the k over 2 all over gamma k over 2 plus 1 times chi squared. And let's assume that actually, let's do chi, we can just do a chi random variable. It's actually the same. So chi squared k of them times pi from j is equal to 1 to k of the square root of your lambda j. Or you could do a chi-squared random variable, that's okay too. So you could do, for example, a chi-squared random variable to the power of k over 2 times pi to the power of k over 2 all over gamma of k over 2 plus 1 times the square root of the variance of gx. And obviously that's probably a point estimate, and you should probably put hat on those, right? So this is the volume of a prediction ellipsoid. And what exactly is this on the right-hand side? Well, the volume of the prediction ellipsoid is just equal to chi squared k to the power of k over 2 times the volume of our associated sample ellipse, right? So that's the volume of our sample ellipse, because we're using our sample eigenvalues and its sample eigenvectors to guide its direction. Right? So this is definitely some of the basic things that you definitely should know on the side of Mahalanobis distances and how it connects to the multivariate normal distribution, and some theoretical and applied aspects associated to, for example, the volume, the distribution of each of these things, especially when it comes to ellipses. So definitely quite a few more things to discuss on this front and some of their applications, but we'll get to them eventually. Hope you enjoyed this video, and I'll see you in the next one. Take care.